Hello students, we are continuing on with our chapter 4, talking about our presentations with chemical reactions. So this is kind of covered over 2 units, units number 4 and units number 5. So for unit number 5, our agenda is going to be, we're going to introduce the concepts of molecular equations, complete ionic equations, and net ionic equations. Now in Unit 4 we talked about precipitation reactions. So in Unit 5 we're going to introduce more types of reactions. We're going to look at acid-base reactions, gas evolution reactions, redox reactions, combustion reactions, and then we're going to classify them and put them into certain types of chemical reactions. There's certain types that these particular reactions follow. So that's kind of our agenda to talk about and to go through in unit number 5. So let's start off talking about chemical equations, molecular ones. So a molecular equation, or also known as an overall chemical reaction, so you'll hear it presented either way, is an equation showing the complete neutral formulas for every compound in the reaction. Okay, so we're looking at this one here, silver nitrate, aqueous, meaning that it is dissolved in water, is mixed with aqueous sodium chloride. And what we see from that reaction is we get solid silver chloride and aqueous sodium nitrate. Does this reaction look familiar? I see an S in there. What does that tell me? That I have a solid, and a solid is a insoluble product, which we talked about in unit number 4. So for this particular example that I'm going to use to discuss the molecular equation, the complete ionic and the net ionic, I'm going to talk about this particular precipitation reaction. Okay, so does this equation look familiar? Yes, it's a precipitation reaction from unit number 4. Now, let's take that one step further and let's talk about a complete ionic equation. A complete ionic equation shows the aqueous ionic compounds that normally dissociate in solution as they are actually present in the solution. What does that mean? We are going to take that silver nitrate from the previous slide, AgNO3, and instead we're going to break that apart into silver and into nitrate ions. Okay, so looking at this equation, I kind of made the arrow red there so you can see what's on either side of the equation. So when we're looking at the complete ionic equation, what we want to do is we want to break up everything into its ions. And what I often tell my students is you can only break up the ones that are aqueous. They have dissolved into the water-based solution and have become ions. As you look at that equation, there's a lot going on in that equation. I want you to look at the subscript S for the solid. Look at silver chloride. Okay, silver chloride is a product. It's a product of a precipitation reaction. It's going to be on my right-hand side of the equation. Notice how it has an S next to it. Notice how those are not broke up into ionic forms. So when they're not broke up into ionic forms, it's either a solid, a liquid, or a gas. We only can separate the aqueous ionic solutions into their constituent ions. So when we look at this chemical equation, I take the AQs, I break them all apart into their ions, I leave any ones that has an S, an L, or a G there for me so that it has to stay together because it doesn't break apart into its ions. In other words, it's insoluble in water, so we're not going to have the ions. We're just going to have that salt in water. So we have the molecular equation, The molecular equation is what we've been talking about in Unit 4. We're going to take that one step further and come up with the complete ionic equation. And then we're going to take it one step further, and we're going to talk about next year the net ionic equation. In a complete ionic equation, some of the ions in the solution appear unchanged on both sides of the equations. Okay, so we see ions that are mirror one another on the right-hand side and the left-hand side. We call these particular ions spectator ions. Spectator ions So to simplify the equation and to more clearly show what is happening, the spectator ions can be omitted. Equations such as the one below, which show only the species that actually participate in the reaction, are called the net ionic equation. So in this particular reaction, I took out the spectator ions that were on either side of the equation. Why? Because I wanted to know what was the net ionic equation. And I tell my students that the net ionic equation is kind of like a business class. When we're looking at what is the net, the bottom line, okay, for the business proposition, okay, would you take your cost and all that stuff associated with it? What is the net amount that you are going to make off of this particular project? It's the same thing for chemistry. The net ionic equation shows me what is the actual chemistry being involved in there. Those nitrates, they were just floating around. They weren't contributing to the reaction at all. But in our case, silver and chlorine were the two ones that were involved in making that precipitate silver chloride. So to summarize, you will need to understand and be able to write a molecular equation, which is a chemical equation showing the complete neutral formulas. You will need to be able to come up with a complete ionic equation, which is an equation showing all the species that are actually present in the solution. So the complete ionic, we break apart all the AQs. And lastly, you'll need to be able to write the net ionic equation, which is an equation showing only the species that actually participate in the reaction. The net ionic equation gets rid of what is called the spectator ions. Okay, so moving along, let's introduce our next type of chemical reaction. Let's talk about an acid-base reaction. Acid-base reactions are reactions that form from water upon mixing an acid and a base together. Okay, so when I mix an acid with a base, I'm going to generate water plus a salt. Okay, and this is always true for an acid-base reaction. When I mix an acid with a base, I'm going to get water plus a salt. Now, when I say salt, I'm not meaning always table salt like is in our reaction here. It could be another salt as what we call like silver nitrate or something like that. Okay, so it could be a different type of salt, an ionic salt. So that term salt is just kind of a generalized term that comes out there. In an acid-base reaction, also known as a neutralization reaction, generally forms water and ionic compound, which we call this salt. Okay, so just remember that ionic compound, just kind of what we call salt. It's not always going to be NaCl. That usually remains dissolved in the solution. Okay, so somehow that is just kind of dissolved in the solution. Because why? Because of our solubility tables. We can actually go back and predict whether they're soluble or not. But for the most part, those ions stay soluble in the solution. The net ionic equation for many acid-base reactions are as follows. H plus OH gives me H2O. H plus OH gives me H2O. This is for many acid-base reactions. For us, this is going to be the net ionic equation for our acid-base reactions. Hydrogen plus OH gives me H2O. The only thing that changes, as we've learned, is the coefficients that are out in front. And we get that when we balance. So let's look at some common acids and some common bases. The number one thing that my students, I try to install in them is when you're looking at a chemical equation, and a lot of times we're just throw these equations, right? Symbols and all this other good stuff. How do we know whether it's a precipitation reaction or an acid-base reaction? So what I have here is some common acids and bases that you can look for. Okay. Now, way back when we named these acids and we looked at them, how do we know that a compound is an acid? We know it's an acid because it has a hydrogen out front. So if I look at the chemical formula for all my acids, they have some sort of hydrogen out front. Look at the base. The bases all have a hydroxide anion to make it a base. Sodium hydroxide, lithium hydroxide, potassium hydroxide, and so forth. So, for this class, you should be able to mix any one of these acids with any one of these bases and come up with a chemical reaction. Next type of reaction we're going to talk about is a gas evolution reaction. Now, a gas evolution reaction is just an extension of an acid-base reaction. Okay, so a gas evolution reaction is an extension of an acid-base reaction. What happens in a gas evolution reaction is that the two reactants make an intermediate product that in a lot of cases is an acid, in which that acid then goes back and reacts with one of the reactants to make a product. And so we get this complicated reaction in which we call a gas evolution reaction. What we have found is that gas evolution reactions follow these particular types of intermediate products and gases involved. If the reactant is a sulfide, we don't get an intermediate product, we just get H2S. If we have a carbonate or a bicarbonate, we end up with an intermediate product of carbonic acid and carbon dioxide. If I start with a reactant that's a sulfite or bisulfites, we end up with sulfuric acid and SO2. If I have a reactant that is ammonia, I end up with an intermediate product of ammonia hydroxide and NH3. This table is going to become extremely important when you're looking at gas evolution reactions. Okay, you're going to need these to look at an intermediate product when you're predicting them. So let's look at some types that undergo a gas evolution reaction. Now, what I want you folks to take away from this is there are several types of compounds that undergo a gas evolution reaction. How do we know something is a gas evolution reaction? And the easiest way to look at these is look at the product side. Notice that one of the products has a G beside it. Okay, so if I was to give you a list of chemical reactions on the test and ask you, is this a gas evolution or a precipitation reaction. Okay, you're going to look at that and say, well, if it has a G, it's going to be a gas evolution reaction, meaning that we have some sort of gas being given off. Well, what would we see as a subscript for a precipitation? We would see an S, right? Because precipitation reactions generate solids. So an S is going to be a precipitation reaction. So if I see an S, it's a precipitation. If I see a G, it is a gas evolution. Gas evolution reactions involving carbonate. We begin by writing the skeletal equation that includes the reactants and products that form when the cation of each reactant combines with the anion of another. What you have to do is you must recognize the intermediate product. Okay, so if the H goes with the CO3, we get H2CO3. That intermediate product breaks down into H2O liquid and carbon dioxide gas. Where did we get that from? We got that from our table. Okay, so we got that from our table. And so we write the corresponding reaction as follows. HNO3 plus Na2CO3 gives me H2O liquid plus CO2 gas. That is from the intermediate product, carbonic acid. And then I just keep the NaNO3 on the end. The last thing we must do is we finally must balance the chemical equation, as we've learned about back in unit number 4, how to balance these. We have to make sure we have the same number of atoms on the left-hand side of the equation as we do on the right-hand side of the equation. So I end up putting a 2 out in front of the HNO3 and a 2 out in front of the NaNO3. So let's look at chemistry and how it's involved in the health. Neutralizing excess stomach acid is one of the biggest things. Tums, different antacids, rolaids, things of that sort. Your stomach normally contains acids that are involved in food digestion. Antacids are over-the-counter medicines that work by reacting with neutralizing stomach acid. Antacids contain the bases such as magnesium hydroxide, aluminum hydroxide, sodium bicarbonate. The base in the antacid neutralizer neutralizes excess stomach acids, relieving the heartburn and the acid stomach. Okay, so these are undergoing an acid-base reaction with these particular ones. Now, the sodium bicarbonate. Sodium bicarbonate is not a hydroxide, so it falls underneath the gas evolution reaction. Okay, so and we know these processes from early on when we mixed baking soda with vinegar. What happens? We get that volcano effect, right? We mix the two together, they bubble up, the stuff comes out of the volcano, makes a real mess, we get a lot of gas involved. What's being happened in that case is we're making an intermediate product with the H2CO3. That acid is then further being neutralized and giving off carbon dioxide gas. So antacids such as magnesium hydroxide and aluminum hydroxide, those undergo an acid-base reaction, whereas the antacids that are using the sodium bicarbonate, those ones are a gas evolution reaction, which we said was an extension of an acid-base. Okay, so we've talked about precipitation reactions, acid-base reactions, gas evolution reactions. Now we're going to talk about what is an oxidation reduction reaction. Oxidation-reduction reactions are reactions involving the transfer of an electron from one element to another. These are called oxidation-reduction reactions, or for simplification terms, we call them redox reactions. Redox reactions are responsible for the rusting of iron, the bleaching of your hair, and the production of electricity in batteries. So this is how your car batteries work. Many redox reactions involve the following reactions of a substance with oxygen. So many redox reactions, we have some sort of oxygen going on in there. Okay, it's oxidizing my system. Now that's not always the case, but for the most part, when we're going to have some sort of oxygen in there doing an oxygen or a redox reaction. The fundamental definition, okay, and these are the key terms that you need to know. An oxidation is the loss of an electron. So oxidation is the loss. If something is getting oxidized, it's the loss of an electron. Just like the fundamental definition of reduction, the gain of an electron is the reduction. Okay, so to help us remember these, a couple mnemonics that are out there that have used have been when we're teaching oxidation reduction is the oil mnemonic oil rig. Okay, so oil rig, what they've used to pull around, do a lot of the fracking in our area and so forth, is oxidation is loss, reduction is gain. Oil rig. Another one is Leo the tiger goes grr. Leo the tiger goes grr. And Leo stands for loss of electrons is oxidation, and gain of electrons is reduction. Okay, so just some mnemonics to help you remember these. Because you're going to be asked, what is the oxidizer and what is the reduction? Which one's the oxidizer and which one's the reducer? So we're going to be looking at these, and you're going to have to look at the definitions. Oxidation is the loss of an electron, and reduction is the gain of electron. Now I know it sounds backwards, right? Because we think if we're reducing something, we would be losing it. Okay, but there is a fundamental reason why this is. Okay, and that's because what's happening is by gaining an electron, we are reducing the positive charge on my atom. Okay, so by gaining an electron, we reduce the positive charge. So we're lowering the charge. Okay, so that's why we use that terminology reduction. I know it sounds a little off because we think of, well, reduction, we would be reducing something. But by gaining an electron, okay, by gaining that electron, we're reducing the positive charge. So notice that oxidation reduction must occur together. We just can't have one oxidizing without the other one being reduced. They coincide with one another. If one substance loses an electron, oxidized, then another substance must gain an electron, reduced. So for now, you will need to be able to identify redox reactions and be able to understand which one's being oxidized and which one is being reduced. A reaction can be classified as a redox reaction if it meets any of the following requirements. Redox reactions are those in which the following occur. A substance reacts with an elemental oxygen. So if I have some substance reacting with elemental oxygen, it's going to be a redox reaction. A metal reacts with a nonmetal. Okay, we talked about metals and nonmetals on the periodic table. What's happening? I'm having a transfer of electrons. Something as simple as sodium chloride. Sodium is a metal, chlorine is a nonmetal. I'm going from the electron on my sodium to my chlorine. I'm having a transfer of electrons, so in this case this is a redox reaction. And more generally, when we just have one substance that transfers any electrons to another substance, so when we have that transfer of electrons, we're going to have a redox reaction. So we have precipitation reactions, acid-base reactions, gas evolution reactions, and redox reactions. Let's talk about our last type of reaction. What is a combustion reaction? Well, look at the first statement there. Combustion reactions are a type of redox reaction. We just got done talking about redox reactions. We kind of introduced some combustion reactions back in the last unit. We talked about that elemental oxygen. Remember balancing those, and I showed you how to use the formulas and so forth, or the fractions, excuse me, not formulas, the fractions to balance those chemical equations. So anytime we have an oxygen, combustion reactions are categorized by a reaction of a substance with O2 to form one or more oxygen-containing compounds, often including water. Okay, so here's the tricky part. What makes a combustion reaction versus what makes an oxidation reduction reaction? They are the same, but what differentiates them? Oftentimes, a combustion reaction will produce water. So for example, we talked about the rusting of our car. Our cars are made out of iron. Okay, they start to rust in the bottom on the frames and so forth. What's happening? It's being oxidized. Okay, so that steel is being oxidized, so it begins to rust. So I have iron plus oxygen gives me iron oxide, gives me that rust. There is no H2O involved in that. Whereas a combustion reaction, I'm taking some fuel plus oxygen, a lot of times like gasoline, mixing it with oxygen, getting carbon dioxide plus water. So a combustion reaction is a type of redox reaction, but you can furthermore classify it as whether it is just a regular redox reaction or a combustion reaction. Combustion reactions will always have the H2O in them. They must include that water. Combustion reactions are also exothermic. What do we mean by exothermic? Heat is given off, right? Why do you think we have a radiator in our car, right? To keep the heat down to a minimum. If I was to drive my car 30 miles, pick up the hood, and then touch the side of the engine, it'd be pretty hot, right? It's undergoing a combustion reaction. So we have an exothermic. Heat is given off. Compounds containing carbon and hydrogen, or carbon, hydrogen, and oxygen, always form carbon dioxide and water upon combustion. Other combustion reactions include the reaction of carbon with oxygen to form carbon dioxide. Okay, so we're going to have some sort of carbon going on in this reaction too for a combustion reaction. So let's classify our chemical reactions. Is it a precipitation, acid-base, gas evolution, oxidation reduction reaction? Or can we reduce the oxidation reaction and say that it is a combustion reaction. Now, like I said before, you're going to see a lot of equations. You're going to need to know whether something is a precipitation reaction or an acid-base reaction or a gas evolution reaction or an oxidation reduction. So how are we going to be able to differentiate these? What does a gas evolution reaction have? It has a gas. So one of the products better have a small g by it. I tell my students, don't get confused by all the stuff going on in the chemical reactions. What I want you to know is to be able to look at them and identify them. So look for the key things. Okay, if it's a precipitation reaction, what's being generated? A solid. If it's a gas evolution reaction, what's being generated? A gas. So look for those S and those G's. Now how can we tell whether something is an acid-base reaction versus a precipitation reaction? Well, how do we know something is an acid? It has a hydrogen out front. So we know one of my reactants is going to be H something, right? So that's how we can differentiate whether it's a acid base or a precipitation. Acid bases have an H out front. I also gave you a table of bases. What are bases? They are all hydroxides, right? They are all hydroxides. So hydroxides make my base. So anytime I have an acid plus a hydroxide, I'm going to have an acid-base reaction. And of course, a redox reaction, I am having a transfer of electrons. So I'll be able to identify that particular type of reaction by looking at the transferring of those particular electrons. The last thing we want to talk about is classifying these particular reactions into what the atoms actually do. Now, we have the specifics of the reaction. Okay, is it a precipitation, acid-base, gas evolution, redox reaction? Let's look at what type of reaction does that fall under. Okay, so we have this umbrella of different reactions. Now let's look at the type of reaction that it falls under. Is it a synthesis or a combination reaction? Okay, now don't overthink into these. Look at the equation. A plus B gives me AB. Synthesis or combination? A plus B gives me AB. Sodium plus chlorine gives me sodium chloride. Synthesis reactions are taking two things, putting them together, and making one. Okay? Oftentimes that would be a redox reaction. What about decomposition? Decomposition is where I take one and make two products out of it. My chemical compound is actually decomposing. Now, what is an example of something that decomposes like this? Hydrogen peroxide is a big one. Okay, so why does hydrogen peroxide in a brown bottle? Because if sunlight was to hit it, instantaneously it would build up oxygen gas. It would separate into its components. Single displacement. A plus BC gives me AC plus B. What's happening is I'm taking some metal, mixing it with something with, say, like a polyatomic or some ionic compound, and that metal is then linking up to that anion, leaving the other metal by itself. That's what we call a single displacement. Again, another example of a redox. Now what about double displacement? AB plus CD gives me AD plus CB. That is a precipitation reaction. Or theorists argue that acid-base doesn't follow double displacement, but for the sake of our class, if we were to take cation, anion, and switch them, right, we would follow the double displacement reaction. So in a synthesis reaction, two simpler substances combine to make a more complex substance. In the series of photographs, we see sodium metal and chlorine gas. When they combine in a chemical reaction, they form sodium chloride. So synthesis is the combining of the two. In a decomposition reaction, a complex substance decomposes into simpler substances. When electrical current is passed through water, the water undergoes a decomposition reaction to form hydrogen gas and oxygen. Okay, this is what's, as you can see, H2O. We've got hydrogen gas and oxygen gas. I'd like to point this out in the picture. Notice how we have twice the amount of hydrogen gas as we do have oxygen gas. If we were to run this particular experiment, it's pretty interesting. That's actually what occurs. In a displacement or single displacement reaction, one element displaces another in a compound. So when metallic zinc is immersed in a solution of copper 2 chloride, the zinc atoms displace the copper ions in the particular solution. Okay, so what's happening is, by putting that zinc metal in there, it's displacing the copper. Okay, so we're having that cation anion switch, but only because the one is just a cation, it mixes with the other anion. In a double displacement reaction, the two elements or groups of the elements in two different compounds exchange places to form two new compounds. A double displacement reaction follows the general form AB plus CD gives me AD plus BC. The kind of reactions that may be a double displacement are precipitation reactions, acid-base reactions, and gas evolution reactions. Okay, we're going to use that concept of cation-anion switch with these three types of reactions in order to be able to predict the products. So, when I look at classifying a chemical reaction, I can classify them into four different types. Is it a synthesis, decomposition, single displacement, or double displacement? If it's a synthesis, I'm taking two things, joining them together to make one. If it's a decomposition, I'm taking one thing, dissociating it into its ions, breaking it apart. Single displacement, I'm using some sort of catalyst or metal in order to split them apart through the cation switches with the only anion in the reaction. And my double displacement is the type of reaction where we just got done talking about, which was precipitation, gas evolution, and acid-base reactions, where we have two cations and two anions and they displace with one another.